Thank you for coming today for the Luke Kathmein's thesis defense. I want to give a quick introduction and a little background for anybody who's not familiar with the way this works. Luke is going to give a presentation that I think will be less than an hour. There will be time for questions from the general audience afterwards. And then we will dismiss the general audience and the committee will stay to ask further questions. And afterwards, as we always say, we will have, regardless of outcome, we will have food and beverages, I guess, is what I'm allowed to say, in Surfside starting around 1 p.m. So Luke came to Scripps about 6.5 years ago after a bachelor's degree in physics at Vassar College and a year in Germany as a Fulbright, on a Fulbright fellowship. And I was thinking just now as I was putting remarks together, grad school has ups and downs, and Luke has fittingly taken that into what he's doing by looking at the ups and downs of the tide. So he's going to tell you about the work he's done to really try and understand how to estimate tides and other types of variability in the ocean, and what it tells us about ocean, the California current, and the system as a whole. And then after this, assuming the committee is in agreement, he's headed off to a postdoc at JPL. So I'll let you take it away, Luke.
Thank you, Sarah. I just have to rearrange a few things on Zoom just to make sure that nothing's getting in the way. All right, well, thank you everybody for joining. I hope you can hear me okay on Zoom. Give me a little message if you can't. I guess you won't hear me say that though. So as you can see, we are in a brand new room because I happen to be defending the start of spring quarter. This is let me pause that one. This is the first defense that's going to be taking place in this room, and you know they say the best for last, and I hope there isn't a corollary where you save the worst for first. So the title of my dissertation is Bayesian harmonic analysis of tidal and wind-driven currents in the California current system. And my committee in charge, this is their names. They're all here, except Bruce, he's on Zoom. Hi, Bruce. So let's see what we got. Okay, so this is just a little structure of the talk. I'm going to go over the background, which is actually probably like half the presentation. And then I'm going to go through Chapter 1, which is building a new tidal analysis package using old math. Chapter 2 is tidal currents in the California current system, characteristics and modulation. Chapter 3, wind-driven currents, diurnal and beyond. And I'm going to give a one-slide summary, and then the acknowledgements at the end as a standard procedure. So apologies for the grainy resolution on this. This is actually the original resolution from the publication. Yeah, it wasn't my fault. So this figure basically encapsulates all of oceanography in one figure. And it generally shows how, as you get larger in spatial scales, you get larger in time scales. So things that take place on the planetary scale tend to take centuries to go through their cycles. And things that take place on only a couple meter time scales might be a couple hours or days. And there's a bit of an outlier though on this axis, and that is the surface tides, which are both very large scale, like basin-wide, but also very fast, that take place at half a day or a day, depending on which constituent we're looking at. And that will actually pose a problem for certain observation systems. So this is that same plot, but now instead we have these little boxes corresponding to observation instruments. So we have moorings, they can't move, so they really have no spatial resolution, but they can go back a really long time. We've had them for decades. And then over here we have a bunch of other stuff. We have autonomous underwater vehicles, and submarines, and ships, and drifters, and floats, and gliders, and they all have these ranges of spatial and time scales that they are able to resolve things at. But I really want you to focus on the green and the purple ones. So the green is high-frequency radar, which we've had for several years, and it says it can't see that far. We'll update that in a moment. But then there's satellites, and satellites are really cool because they can see the entire world, basically, because they orbit around the entire world. And so that's satellite oceanography has been sort of pretty revolutionary in the last few decades. But there's a fundamental constraint that satellites have, and that is that they really can't break the laws of physics in orbit any faster than they're allowed. So they can't resolve timescales below a certain level. I mean, in principle, you could like send dozens of satellites up, but that's a billions and billions of dollar proposition, and you're not going to get that funded. So let's put those two boxes of radar and satellites over the ocean processes before that I showed you. And this publication from the figures was from 2005, so that was before the HFR, the high frequency radar network, got really big. So we could probably drag this box to the right. It can see out to about 100 kilometers now. But no matter what, we're still going to miss the surface tides, and satellites are always going to miss the internal tides and the surface tides. So what are we going to do about that? Because they are still contributing to the overall variability that the satellites observe. You just can't resolve the processes directly in the time domain. So let's talk about the tidal life cycle, shall we? From birth to retirement. So when the sun and the moon love each other very much, they exert a gravitational force on the ocean, and this generates baby tides. Now, unlike humans, who generally get larger as they grow up, both vertically and horizontally, tides do not. They do actually the exact opposite. They start big, and then they shrink, and they diminish as they get older. So we start out with the barotropic basin scale tide, which is the tide that we, the surfers care about. It's what you see when you go to the beach. Maybe it comes in and washes your picnic away, I don't know. And then when that large tide washes over underwater features, like in this diagram, it leads to propagating internal tides because the ocean is stratified. And those tend to occur at wavelengths less than about 200 kilometers, which is much smaller than this. And then eventually they will be modulated by stratification and currents as they propagate through the chaotic, noisy ocean. And then eventually it leads to turbulence, which leads to ocean mixing. And so the tides actually are an important contributor to how mixed the ocean is. But we're going to focus on looking at these three from observations. We're not going to look at turbulence, and we're not going to worry about gravitation. And I have these nice little animations that NASA was so kind to make. So this is the barotropic tide. So just so you can get a feel for it, you see how it's just orbiting around the basins, and it's pretty big. And at the bottom, that's hours, minutes. And you can see they're everywhere. And there's really not much else to say other than that they are very strong and very fast compared to their size. However, internal tides, like here, let me start out here, off the line. Internal tides have the same frequency, but they go over much shorter. Hold on. Give me just one moment. I need to do something quickly on Zoom. I think it isn't recording, but you're probably recording on. Okay. So you can see here now that the internal tides, they're at the same frequency as the barotropic tide at first, but they propagate much more slowly because their wavelengths are so much shorter. And so you can see that they have a very different character overall from like how they behave. But they're at the same frequency as the barotropic tide. So any satellites, any observation network will see both of them at the same frequency, but different spatial scales. And this is a backup in case the video didn't work. So tides are known frequencies with predictable phase, and they can be removed from satellite data, and they've been doing that since the 1980s. So crisis averted, we know what the tides look like from first principles, so we don't really need to worry about them in the satellites, for example. Well, wrong. Recall we have step 3. We recall that the total energy of the internal tide has a substantial component that is not locked in phase to the astronomical forcing. And it's due to the modulation scattering of the propagating tide by the mesoscale processes in the ocean. Now, how bad could it be? Well, about this bad. So this is the fraction of mode 1 baroclinic, or internal, semi-diurnal sea surface height variance, considered to be non-stationary from these various satellite missions. And this is something Ed Zarin did back in 2017. And he basically he combined harmonic analysis with analysis of long-track wave number spectra. And found that basically, depending on where you're looking in the ocean, the tides can be completely stationary and coherent, or completely not. That will be a problem because as we have satellites with finer resolution, which I'm going to look at in a moment, the smaller scale modulation that we expect to happen from smaller scale processes will start to become important. Also, I want you to look at Hawaii really quickly, where we know that internal tides are generated, and that is it's very locked in phase to the moon because it hasn't propagated far enough away to lose its predictability just yet, but it starts to lose it, say, out here in the middle of the Pacific. So this is sort of the previous state of satellite altimetry. This is sea surface height from 7 meteor altimeters And then this track is the SWAT satellite track, which I'm going to show you in just a moment. But I want you to just get an idea, like this is the resolution of features in the ocean that we were previously able to observe. And this is what SWAT can do, and this was just a few months ago, and SWAT was launched in December, so this is quite revolutionary, really. So we're able to see these processes at much finer, like 10 times the spatial resolution. And as you can see, it's it's the same process as, we got the dark red here, and we got the dark blue here, and we got in between here, but you can actually resolve what's going on. So it's quite remarkable. And just to drive the point home, here's the image from a different point in time, and I just want to include this slide because I like how the French call it Le Gulf Stream. This is a different day. This is just last month, like 3 weeks ago. Wait, I had something else to say. Yeah, so with SWAT and presumably future Earth-observing satellite missions, it'll probably get even better. Understanding smaller scale features in the ocean will be more important for interpreting signals. In summary of the problem, tides are energetic and they're everywhere, and they're too fast for satellites to resolve directly. Some tides are very predictable, but others are not, and they occur at scales that new satellites will resolve. So understanding them, for example, how energetic they are, or their spatial scales, is going to be important to interpreting satellite data. But tides aren't the only fast process in the ocean that also complicates satellite observations. We also have diurnal processes that are driven by the wind, and so this is going to give a little second thought to this. So diurnal, which is to say daily, 24-hour winds and currents, are energetic, and they pose a similar problem as tides for scatterometry. So scatterometers are instruments that estimate wind and or current vectors via backscatter. And when they're on satellites, they're usually sun synchronous, so they orbit the same point on Earth once a day. And when you're doing a daily sampling of a process, you want to avoid sampling it where it is at its minimum. So if you think about just some schematic of a daily diurnal process, if you happen to sample it right when it's at 0, you won't get any of the energy in your overall signal. Now, no matter what daily sampling, you're going to alias it to a constant, but it's best for you to get as much energy from that signal as you can. So this is another problem. So basically, high-frequency processes are harder to see by satellites. So we need frequently sampled data with spatial resolutions at least as good as satellites have, and we have that network. This is the high-frequency radar network. This is a picture I took a couple years ago for a presentation. I lost the original picture, so I just have to copy the slide over every time I make a new presentation. And that right there on the right is the high-frequency radar antenna that we have here on Scripps campus, just down the hill, and these exist all but none of the clouds I'll show you. But this is a schematic of how they work. So this depicts Bragg scattering processes that allow for ocean current measurements with high-frequency radio signals. So it bounces out radio signals, it bounces off the ocean surface, and it comes back, and this echo, the antenna is used to estimate where the current, how fast the current is moving, but only in the direction looking to and away from the antennas. So this is the growth of the network over the last decade and a half or so. So in 2005, we had a lot fewer than 20, but just before 2020, we had like 170, and the network just keeps growing. And it's got to stop at some point. But the red lines are ones that have been taken out of commission. So as you can see, most of them are still running. So it's really sort of revolutionized how we've seen like coastal oceanography. So they're near real-time vector surface currents, use the Bragg scattering at these radar frequencies, and they are, the way that we use it is after they've been processed to have their radial observations gridded to 1, 2, and 6 kilometer grids. We use a 6 kilometer grid because it can see the farthest offshore. So this is what one radar antenna sees. It sees currents if they're moving away from it or towards it. Well, that's not very useful because the currents in the ocean are moving every direction. What are we going to do? Well, we're going to set up several dozen antennas along the coast and then do a little bit of trigonometry, and then we're going to get an actual real vector field with some error in terms of how we estimate it. But this is what we use. This is off the coast of New Jersey. So we have a problem, we have a data set, now we need a strategy, and this is just sort of a little bit of background for anybody who are a little bit rusty on some of the ways that we analyze ocean time series. So we want to pull tides out of the energetic ocean. So tidal fitting and prediction is an old topic, and it motivated the development of a subfield of mathematics called harmonic analysis, and it also motivated the invention of these wacky old computers, analog computers. So like these are 10 different constituents, so you like adjust the knobs and you turn the crank and it tells you what the tides are going to be like in the future. So I thought that was kind of funny. And we're not going to focus on those wacky computers, we're going to focus on the harmonic analysis. Let's see, so to define what harmonic analysis is, the American Meteorological Society has 2 definitions. They have this one that's sort of more broad, and I'm not really going to focus on this very much, except maybe QU on the keywords amplitude, period, and spectrum. We're going to look at power spectrum in a moment. But they also have a second, tidally focused definition, where you want to represent the tidal variations as sum of several harmonics, using the word in its definition, brilliant. Each of several different periods, amplitudes, and phase. The periods fall into 3 tidal species. There's long period, and the diurnal, which is daily, and the semi-diurnal, which is twice daily. We don't really care about the long period because the satellites can fully resolve those. It's the other 2 that are more important. So just as a reminder, again, this is a schematic about how a wave works, as wave anatomy. So the amplitude is how high it gets at its peak. Period is the distance between peaks in time. Frequency is the inverse of that. And then phase is just the fraction of a full cycle that your peak is shifted from some arbitrary 0 point. Phase is kind of arbitrary, but we define it in different ways depending on convenience. So what is a power spectrum? It's a type of harmonic analysis. So when it's, I'll show you examples in a moment, but by definition, it's basically when the power in a signal is broken down by frequency. Well, what's power? I just want you to go off of an intuitive feeling. Just go off of vibes. So power is just like how strong a signal is. And every signal in time has an equivalent representation of frequency, and every signal in space has an equivalent representation in wave number. And oceanography isn't the only field that uses power spectra. You can look at them to sort of mathematically describe certain things that you kind of fundamentally know. Like, you know that a flute and a trombone sound different. But why do they sound different? Well, their sound waves are shaped differently, and you can more accurately or more conveniently describe that by looking in the frequency domain. So the power spectrum of a flute sound is very different looking from that of a trombone sound, but and astronomers use this too. This is the spectrum of intensity from the sun, both before and after it goes through the atmosphere. And after it goes through the atmosphere, you can see several visual absorption lines from different compounds in the atmosphere. You got your water, you got your carbon dioxide, I hear that's a big one. You got your ozone, you also got Rayleigh scattering in the atmosphere. And then even, cosmologists use these. This is a red-shifting light from a distant quasar through hydrogen clouds, leading to the sort of famous Lyman alpha forest that cosmologists are familiar with. But we're oceanographers, we don't deal with that. We're going to look at power of spectra of ocean processes. So this is Scripps peer pressure, not to be confused with the peer pressure I exerted on half of you to come to this defense day. And this is the quantity that surfers care about. It is the it's basically water height, but observed via pressure. So you put your pressure sensor at the bottom of the pier, it tells you how high the water is. And if you want to zoom in on the first 3 months of this record in 2021 and 2022, we have you can zoom in and see the daily variations of the tides, the ups, the highs, and the lows. We also see this spring neap cycle where there's constructive interference between the 2 constituents we can talk about later. And then there's destructive interference in the purple zones. And just as a refresher, this is when if the sun and the moon are aligned, it's a spring tide, it has nothing to do with the season. And if they're at right angles, and it's a neap tide because they're counteracting each other. And the complexities of like orbital tilts and ellipticities of the orbits is what leads to a lot more harmonic constituents than the 2 you might expect from just having the sun and the moon. And this is what the power spectrum of that time series we just looked at looks like. So what we'll see is these tidal constituents, they have these sort of arcane like names where you have like a letter and then a number at the base of it. And that number describes whether it's in a 1-day or 2-day cycle. And the letters are kind of arcane. I looked up at the NOAA Tides Handbook and they said, well, Charles Darwin's son came up with these and living in the shadow of his father, I suppose. And the M stands for moon and the S stands for sun, and the other letters are they couldn't really make heads nor tails of them. But they're these discrete peaks on top of this noisy background. And would you look at that? If you look at it in, if you look in log space, the frequency is the power at non-tidal frequencies is proportional to some power of the frequency. So in this case, 1 over the frequency, or frequency to -1, and that will be important later. So we have a problem, which is tides and similarly periodic wind-forced currents are faster than what satellites can resolve, and they can't all be removed. We have this nice data set that we're going to be looking at. High-frequency radar, it is similar to a satellite, but it is stationary and local and rapidly samples, so it's not actually similar to a satellite at all. And then we have basic knowledge, which is periodic processes appear in a power spectrum as spike, and it's the first step towards isolating them. So we're going to now go into chapter 1, which is another tidal analysis tool, because there are already a lot of them, and we're just adding one more to the mix. This is published in the Journal of Atmospheric and Ocean Technology last year with 3 of my committee members as co-authors. And I'm going to be skipping over some results from this because you can look this up later on your own. So, overview, we're going to be explaining why standard harmonic analysis techniques are sometimes inadequate. And then we're going to be taking an older mathematical framework for parameter estimation and applying it to tides. So, recall the power spectrum, we just looked at it about a minute ago. What if we want to predict the tides out into the future, or isolate them from the surrounding noise, or fill in a gap that we're maybe missing in the data? Well, power spectrum can't do that. It can just tell us how much power it thinks is at approximately the right frequency. I want to point you now towards the noise term, first of all. Remember I said, oh, well, the non-tidal process in the ocean can, sort of broadly described as following this straight line in log-log space. Well, we actually have names for the color of noise. So we're going to turn this into dark mode for a moment. If your signal is proportional to the frequency to the power of -2, we call it red noise. And if it's to the -1, people call it pink noise, because it's the average between this and white noise, which is not a function of frequency. It is constant spectrally flat. This is like, it's white noise. And then blue noise is when you're increasing in power with increasing frequency. And everybody knows that the ocean is a bright shade of red. Processes in the ocean tend to, and all geophysical processes, have a red spectrum in general, because longer period processes are just more energetic than the smaller scale stuff. So if you want to predict the tides, let's shelve that whole noise discussion for a moment. Let's look at this sort of nice little basic framework we have. We have our data is represented by y, and we're going to model it as the sum of all these sines and cosines at frequencies that we prescribe, tidal frequencies usually, but not necessarily. We can put in more ones if we want. And then r is what we expect to not be able to be modeled, residual, non-tidal noise, we call it. It's sort of, I'm playing fast and loose here because it's not really noise, because it's not instrument noise, but I call it noise because it's not the tides. So that leaves us with this unknown harmonic coefficients, and these are numbers that basically tell us how strong the sines and cosines are to add up to get the tides. And in order to find x, there's the standard technique is ordinary least squares, where you find the x that minimizes the sum of each r, sum of the squares of the r, of the residual. And so this is the solution. Don't worry about it, and don't worry about why it's wearing a little hat. That'll come up later. It's basically just, you rearrange the h in a couple different ways. You multiply it by the data, bada boom, bada bang, you got the harmonic coefficients. And so this is the first month of that time series I was showing you earlier, Scripps peer pressure. And, okay, well, it looks kind of how we expect. And if we do that procedure with ordinary least squares, we get this red curve. I hope that's easy to see on the screen. But basically, if we just take those first 6 peaks in the spectrum that we expect the tides to be at, and then we fit those frequencies, then we get this, and it looks pretty reasonable. Look at that; it pretty much models it exactly. There's some misfit and stuff, but that's okay. I think this is good for projecting the tides out in the future. But not all data are this easy. So. There are 2 problems with ordinary least squares. It is not regularized, which means that your model is not constrained, and it can basically do whatever it wants in order to minimize r squared, including blow up, and we'll show you an example of that in a moment. It is also not weighted, which means that when you're solving for x, you're assuming that r is the same everywhere and that it is spectrally flat. That's white noise. So the noise assumption is coming up again. So it assumes white noise when in reality the actual ocean has red noise as background. Now for really strong signals, it doesn't matter, but this is a little bit more of a messy signal. This is from high frequency radar, which we're going to be looking at in a moment in the next chapter, but I pulled it out here. This is the zonal component of somewhere off the Southern California coast. Can't remember exactly where. And if you do an ordinary least, it's actually okay because we have a lot of data, and this tidal signal is fairly strong. But let's say we want to fit to the tidal peak as well as the very nearby frequencies to maybe see what they're doing. And I don't mean like tidal frequencies. I mean very nearby frequencies, spaced by as tight as we can get with this record length. What if we now take out some of our data? I've graded this out. What if you have a big gap in your data, but you still want to analyze it at this set of tightly spaced frequencies? Well, let's see what happens. You notice a problem. There's a major problem. It blows up, and that's not supposed to happen. You know that that's not physical, but ordinary least squares doesn't know. It's just like, hey, boss, I minimized the residual like you told me to. Well, it did its job out here, but you know that because it blows up here, it's probably just nonsense out here that's sort of assembled to look correct, but it's not. So what we need to now do is regularize it. And so mysteriously, if we just include this little extra term of the right size, it actually works a lot better. It's still not perfect because
you're missing the data there, so it's not going to get it right. But it doesn't blow up. And I skipped the slide where there's going to be the frequency domain explanation of this because it just took too long, but you get the phase correct with the green solution, but you don't get it correct with the orange solution. And so this is an improvement. And so the question is, how do you do this systematically? Well, you don't do it with ordinary least squares. You have to go down a darker route. So if you recall, our equation, we start, this is the same one. Now I actually have to distinguish between whether X is wearing a hat or not. So hatless X is this sort of assumed to be a true value that the universe is like hiding from us. It's buried in there somewhere. And our X with a hat is only our best estimate of it, our guess. And how we achieve that is sort of our choice. And so instead of minimizing R squared, what if we minimize the expected value of the square of the difference between what we can calculate and what the real value is? Well, that kind of sounds nonsensical because we don't know what the real value is. So we don't really know what this is, but we can guess it statistically. So what we then do is calculate X hat as the Bayesian maximum a posteriori estimate, requiring that X and R have independent Gaussian distributions that satisfy conditions under which this map estimate gives X hat. So in normal human language, basically, we're using known or assumed statistics of the data to inform our solution. And this is the solution we get. I skipped the derivation. It was incredibly boring and long. I mean, not long like in the grand scheme of like mathematical derivations, but too long for this presentation. And it looks the same as ordinary least squares, except we see these two extra terms pop up. We see this R matrix and this P matrix. And these are the expected covariances, covariance matrices of the residual and our harmonic amplitudes. So how do we calculate reasonable R's and P's? Well, we can take it from the power spectrum if we think we have a reasonable power spectrum. And if we don't, well, we can just make one up. So we prescribe frequencies for fitting in some vector omega. And then we also prescribe the slope of our noise. Here it's clearly -1. And we take the power spectrum at these tidal peaks, and we define our P as that after doing a little bit of normalization to get it to the right units. And we do this basically the same procedure for this. We take this the spectrum, we inverse Fourier transform it to the time domain because that's important, and then we renormalize it to a reasonable value, and then we get our R matrix. And so this is sort of the heart of what we did to make our tidal analysis package. So in the context of other tidal analysis packages, T-tide reigns supreme. It uses ordinary least squares and other improvements. I'm sure any of you who have done ocean time series analysis have probably had to use T-tide, and it's good. It really is great. There's NS-tide for river tides, and there's U-tide for this other improvement. And we named ours because it uses red noise assumptions as red tide. It has nothing to do with a toxic algae bloom called red tide. I just named it this partly because it makes sense and partly out of mockery for all the slick, clever acronyms people come up with for their projects in science. So I wanted to name mine after toxic sludge. So for many purposes, it's not actually that important to make these assumptions and be that careful. If your signal is strong, much stronger than the background, then you're probably good. If your background is nearly white noise, well, that's what ordinary least squares assumes anyway, so you're probably good. But sometimes it is important, as I just showed you, if you have a gap, or if your signal is kind of comparable to your background, and so the noise is an important term to consider, or especially when the background spectrum is steep and like to say frequency to the -2, for example, or more. And see paper for more comparisons of how ours compares to ordinary least squares. So in summary, I've spent long enough on this chapter. Harmonic analysis is how we obtain information about the tides. Sometimes the easy approach is not the way to do it, so you have to take the hard route. And our package uses knowledge of data, the statistics of it, to inform and constrain the solutions of harmonic coefficients. Okay, so let's apply that to actual data and see cool results. I color-coded the chapters in case you didn't notice, so you know where you are. So this is a work in preparation. It's nearly ready for submission. The proper title is Characterizing Non-Phase Locked Tidal Currents in the California Current System Using High-Frequency Radar. Pretty descriptive. So our motivation, recall, and as internal tides propagate, they lose predictability. They become difficult to remove from infrequently sampled satellite data. So let's examine this component in the California Current System and the tides in general. So tidal modulation signatures in the frequency domain, we're going to look at that really quickly so you know what to look for. We're going to use the finite element solution 2014 barotropic tidal model to compare to and remove the barotropic component because we're interested in the baroclinic internal component. We're going to look at what the tides look like in this region. We're going to look at how much of their variance is phase locked or not. And then we're going to compare the modulation of two tidal constituents to show you that what's going on. So it's just a little schematic. what does a non-phase lock tide look like? Well, it doesn't look like the first one, although this is like it's a tidal modulation disguise. So this is, or it's pretending to be, but when it isn't. So this is actually two tidal constituents independently adding on to each other linearly and creating what looks like a modulation, but it isn't. This is the spring neap tide cycle. But actual amplitude modulation in the frequency domain looks a little different. And even if in the time domain it looks the same, you'll have these two little peaks on the side if you're modulating it at a single frequency. And the spacing of these peaks is related to the frequency of the modulating envelope, which I've plotted here in red. But of course, the ocean is a lot more complicated. In general, we'll see modulation by a more chaotic process like this, which has its own red spectrum. And the spectrum of the tide then will be, it'll have this central tidal peak as we expect, and it'll have this cusp. And the width of the cusp is actually related to the time scale of the modulation. So let's apply this analysis that we had in chapter 1 to all the data that we have in for the tides in the California current system. And this is what we get. I have zoomed in sort of on the 6 high energy bands within what we can resolve. We have very strong annual cycle, no surprise. And then we have these different tidal peaks. And the S one we're going to look at later in chapter 3. So don't worry about that. This is not even a tide. This is it's an imposter. This is wind driven. And then we have the O1 and the M2 and the S2. And you see the red here is a nonlinear least squares fit to this data, which is in turn the amplitude of a linear least squares fit to the data, which is in turn gridded via a different least squares fit. It's least squares all the way down. I don't know where reality begins. But from this least squares fit of least squares fit of the least squares fit, we get these timescales of modulation. And we see 218 days for the O1, which is, we'll get to that in a moment, and then 243 days for the M2 and shorter 181 days for the S2. Now at this latitude, M2 and S2 are super inertial, so they're propagating internally, but the O1 isn't. And I want to point out something is that what we see here in the M2 and S2, but not in the O1, is these little annual modulation peaks. And that's indicative of amplitude modulation or possibly phase modulation by an annual process. But that doesn't happen to the O1 because it's not propagating internally. So it doesn't feel the stratification in the ocean changing seasonally the way that these two do. So we're going to be focusing on these two, especially the M2. But I'm going to show you maps of this non-propagating tide, this non-tide, and this more important propagating tide now on the next slide. So I'm going to take these peaks and put them on the map. So this is what we get. I also have plotted tidal ellipses over these, but let's not worry about that right now. Just look at the colors. So we have the O1 tide, which is coastally trapped or limited basically, and weaker than these others. The S1, the wind-driven diurnal, is very intense here in the Southern California bight, as well as certain regions along the coast, and it seems to be coastally limited. And then we have the M2, which is not coastally limited, but it does have hotspots of what looks like generation sites. So here at the Mendocino Ridge and the mouth of the Columbia River and the San Francisco Bay, and also here in the SoCal bight. So let's look at plot C without the ellipses and look what it looks like before and after we remove this barotropic tide model that I talked about earlier. And as you can see, it removes a lot of the energy. So a lot of this energy is barotropic and in principle removable via this model from satellite data. But we still have these hotspots left over and we still have these sort of interesting propagating features. Well, let's look at the phase of the tide then to sort of get a handle of what's going on. So this is the phase of the V, so the north-south component of the velocity at the M2 frequency. And this is what the data see. And so it's mostly grouped around this sort of the blue 45-degree phase, which is actually what the tidal model predicts. But we also see these 30 to 50 or so kilometer features on top of it, which indicates propagation. So if you subtract the barotropic model from the observations, we get the phase, we get the difference, and then the phase of the difference is very similar to, and well, because it is, internal propagation. And if you're not convinced, let's animate it. So unfortunately, I have to really quickly loop the video manually. Okay, so this is what we see in the data. I would just want to point out how remarkable this is, because this is not a model. This is real, honest to goodness, observed by an antenna data that we're getting from the ocean. And you can see sort of this big, it's red, it's blue, it's red, it's blue. That's the barotropic tide that's sort of, sweeping up and down the coast. And then we have this slower, much slower, smaller scale propagation along, in certain regions. I'm going to step away from the computer and point out a few features. Actually, no, I'm going to point out the features on the next one because we can remove the barotropic tide and animate it where you just see the propagating component. So sorry for the people on Zoom. But we have right here, this is the Mendocino Ridge, and you can see how there's internal waves propagating northward, and there's also waves southward. It's what we would expect. And we see that similarly elsewhere, but sort of also the mouth of the Columbia River has this interesting sort of signal coming out of it. And also San Francisco Bay, it looks like it's perfectly out of phase, outside of blue here when it's red. And similarly, we have all sorts of interesting chaotic stuff going on down by in Southern California. But yeah, this is real data. This is not a model. And so we see this propagation. Okay, so we know we have propagating tides. Oh, nope. There we go. So now let's look at the fraction of variance that's phase locked. So apologies again to the Zoom people, but I forgot to include this figure in the presentation, so I just drew it on the board. So yeah, I know. What we count as phase locked is kind of, there's really no standard definition. People sort of do different ways, but they're all in the same spirit of, if it is at the tidal peak and predictable, so here's in blue, then it's phase locked, and if it is not, for example, it's that wide cusp that I drew earlier, it's non-phase locked. So this is basically the fraction of this blue peak plus the red. So where this is close to yellow, that means the peak is dominant. That means the M2 tide is super duper predictable and in phase with the moon and at that frequency. And where it's blue, it starts to break down. Now, in some places where it's blue, this tidal signal is just weak in general, so you don't actually have to worry that much about it. But in some places, not so much. So if you remove the barotropic model, which only hits the peak because that's where the barotropic tide is dominantly at, then we get this map. So you can see an increase in non-phase locked fraction, or a decrease in the phase locked fraction of total tidal variance within this frequency band. And you can sort of see how it shifts. So this blue histogram corresponds to this map, and the red one corresponds to the second map, and it really shifts. So like you get from around 60% coherent energy on this plot down to like 20% on this plot with this sort of spatial variability in it, which is about 100 some kilometers. So SWAT will be able to see this. Okay, so is there anything notable about how the M2 is modulated? Well, yes, there is. So what I did here is I took those, I estimated the envelopes that modulate the M2 tide, and then I did the same thing for the S2 tide. And then I compared them, and I took the correlation coefficient of the two to see how similar they are. And the reason I did this is because the M2 and the S2 are very similar frequencies, but they are forced by totally different processes. So one's by the sun and one is by the moon. So any modulation that they have in common are probably going to, well, no, they're definitely going to be in the ocean. It's not going to be some sort of astronomical artifact. And where you see it not hashed out, so especially the dark red, is statistically significant. And you'll see I selected these 5 little points. So now I've plotted these intervals for you. And so you can visually now compare in the time domain these locations that are particularly correlated. So for example, in the mouth of the Columbia River, we see this annual modulation of both tidal constituents, presumably by the Columbia River plume, which is a strong seasonal cycle up there. It's like a classic coastal oceanography thing that they teach you out here. And then elsewhere, it's not as periodic. It's a lot more broadband and red noise like. But they are, in fact, very similar across all those locations, and we don't necessarily expect that unless we expect the stratification to be modulated both the same, and it basically is. So this points towards possibly predictability. If we know how it's being modulated by the stratification, then we can sort of predict how the tide is breaking down, and so we can get this from that potentially. So conclusions. Tidal surface currents, we isolated them and found them to be modulated at about 200-day timescales, and as well as the annual timescale. Barotropic model reasonably estimated the barotropic component and left behind a baroclinic and less phase-locked tide that seems to be propagating. And the M2 and S2 have correlated amplitude modulations, and this points towards an underlying modulating process and potentially predictability from it. We did not address the predictability component, but we sort of pointed towards that. So let's look now at the final chapter, which is wind-driven diurnal currents. So we're using similar techniques looking at a different process. So this is another work that is in preparation. It's not as far along as chapter 2, but it has some interesting results. So it's a diurnal cycle in the California current system, currents from high-frequency radar, and winds from ERA5. So I'll just say right now, ERA5 is a reanalysis product by the European Center for Medium Range Weather Forecasting. I think I got that right, I'm not sure. But they produce this, they produce a lot of climatological quantities that you can analyze. And we are analyzing the 10-meter wind speed, which is a pretty standard quantity that people look at over the ocean for air-sea interaction. So recall that diurnal processes pose similar problems for certain satellites, scatterometers,
And we want to know when currents are strongest, their spatial structure, as well as potentially any seasonality we need to worry about. And also, what else can we learn along the way? So we compare currents with winds, and we focus on the daily cycle. We examine when time of day they're both their maximum, the coherence between them, which is basically correlation in the frequency domain, and the deflection of current, this angle. We'll talk about that in a moment. So, more power spectra. The color is the wind power spectrum, and then the power spectrum in black is the currents clockwise, and in gray is counterclockwise. So these are rotary power spectra, which are power spectra that are broken down by the direction that they're spinning, which is more useful for this because both these processes in the ocean, wind and current, well, the wind isn't in the ocean, both these processes on the Earth tend to be polarized and spinning mostly in one direction, and that is clockwise. And I just want to compare these two power spectra real quick. You can see that both have a very strong peak at the diurnal frequency, and that's what we're going to be mostly looking at. We also have the near inertial response here at this latitude. It produces this strongly clockwise peak. And as you can see, the wind and the current both have different noise slopes. Good thing we have a tool that can actually address that. So now if we look at the amplitude of the wind on the left and the current on the right, we can sort of compare the general landscape, or seascape in this case. So we have coastally intensified winds, really strong down here, kind of elliptical. We have coastally intensified currents, really strong down here, pretty elliptical. Okay, well, they're pretty similar. I will point out, though, the current is a little bit more circular than the winds. And black ellipses are summer, and white are winter. So it's also weaker in the winter than the summer. But this is sort of an overall, it's like a literal top-down view of what the winds and the currents look like at the diurnal frequency, seasonally, in our domain. Coastally intensified, you get the picture. So how strong are the diurnal processes relative to the other processes? Well, as a fraction of total variance in the summer, it's stronger than in the winter, and it is still coastally intensified for the wind, as well as for the current. You see the same thing, basically. This is the fraction of variance that is at the diurnal. And in fact, in some regions here, it's 50% of the variance of the current is diurnal. So it's a pretty strong process we got to worry about in some regions. So when are they at their maxima? So seasonally, summer, winter, left, right. For the winds, we have the hour of the day, the local time, at which they are at their maximum in their cycle, in amplitude. And you can see, well, it sort of propagates offshore. It's in the 3 to 5 o'clock range near shore, and it gets later in the day as you propagate outward. And it's fairly similar for summer, winter. But this is the time where, like, within 62 kilometers of the coast, that's the 2 grid cells in this model. Then it's in the 4 a.m. p.m. for the summer, and 50 minutes later for the winter. And this is consistent with our understanding of the sea breeze, land breeze phenomenon. But the ocean currents is a little bit more chaotic than that. So in the summer, it's kind of every direction. And you may think, oh, well, great, it's hopeless. No, it's not. It's not hopeless because the currents, as I pointed out earlier, are mostly circular. And so that means their maximum and minimum aren't that different. So where the currents are most circular, you don't really have to worry about when you're observing them because you're going to be hitting at their maximum anyway. But then during the winter, the ellipses tighten up a bit and they become more eccentric. So it does matter then when you sample them. And it turns out during the winter, it's basically at the same time as during the as the wind, but a little bit different time. And there is spread, and they have similar distributions in this. But moral of the story: if you're worried about at least the California current system, sampling it for wind and currents, you probably want to hit it around 4 to 5 o'clock range, on top of presumably other considerations you have for designing a satellite orbit. So how coherent are the winds and the currents? Like, if you know one, how much can you sort of guess at the other, at the diurnal? Well, we could look at the U's and the V's, or their cross terms, but we're not going to. We're going to look at the rotating vectors. So we're going to look at just the clockwise and the clockwise. So the clockwise wind, how coherent is it with the clockwise current? Because they're both dominant clockwise. And this is what we get. These plots on the left are summer, on the right is winter. This is the coherence, and this is the phase. I'm going to talk about this, break these down. So what we see here is a lot of very red values, and that means that this is very highly coherent. The wind and the currents at the diurnal frequency are very coherent in their clockwise components. For both winter and summer, and there's not that much of a difference, really, winter and summer, so we could break down, split hairs about it, but we're not going to. And then the phase is basically how different they are in their cycle. And that is, again, similar in summer and winter. So the moral of the story here is basically that they're highly coherent, and they're they're somewhat related in phase, but there's a spread from about 1 hour to 9 hour difference in when they're at their peaks, or when they're in their cycle. Oh, and I just want to say, I did not show this, but there are plots of this for other constituents that we expect, other frequencies we expect not to be coherent, and they are not coherent. So this is not spurious coherence. This is real. Okay, so the clockwise winds and currents are very coherent. Does their phase, so where in the cycle they are relative to each other, translate to some physical angle in space? And the answer is pretty much yes. So what I'm defining as the deflection angle is the angle between the wind when it's at its maximum and the current when it's at its maximum. We see more variation near the coasts during the summer in this angle. Sometimes it's basically 0 degrees. Sometimes it's more than 90 degrees at the same time. And then the distribution of angles shifts seasonally a bit, but I'm not entirely sure how important this is. But what I think is important is that there's very little seasonal change in the Southern California bight, where we noted earlier that both currents and winds are at their strongest locally. What do we actually expect? Like, is this totally unexpected? Well, classical Ekman theory, which is a steady wind over the ocean, predicts a 45-degree deflection angle. And if you recall, well, 45 degrees is this blue color, and that blue seems pretty predominant here in this domain, but not everywhere. We see 45 degrees, but only regionally, like in Southern California. There are more sophisticated models than Ekman. They're still idealized, but they explain a little bit more. But they don't quite explain everything that we see. So if we now plot,
hold on, no, sorry, yeah. No, I'll skip that part. So anyway, this is now that angle I was telling you about between currents
and winds as a function of frequency, and plotted next to this model that one of Sarah's previous students came up with, Chanelipo, and that is in the dark gray. And so that sort of tells you, well, maybe this is what you could expect. And what we see is sort of a general tendency towards this 45-degree deflection angle, but not quite. It's lower than that at low frequencies, and it overshoots at higher frequencies, with the diurnal being particularly anomalous. And in the winter, it's closer to the 45 degrees than it is in the summer, which is interesting.
And overall, in the error bars are the inner 50% or inner 90%. And overall, so there's this deviation, but sort of general agreement. And this might point towards a better understanding of the physics of
Earth interaction in this region. So what does this deviation in deflection angle mean? Well, at the diurnal, it's among the largest deflection, and one hypothesis is that it's an influence of diurnal heating of the mixed layer. However, at other frequencies, we don't expect that there's no peak in the frequency of the heating of the mixed layer at these frequencies. So the deviation is similar to what we see in previous observations like drifters.
And this difference that we see between, say, offshore and onshore angles, which seem to be one feature, is it could be because of different depth varying eddy viscosity onshore and offshore. It could be wave-induced Coriolis-Stokes forcing because the Stokes drift is stronger farther away from the shore than is near shore. At least that's what I think, based on the plots that I looked at. It could be something to do with complex eddy viscosity, which could rotate the vectors more. So basically, it's pointing towards potentially more physics that we need to investigate. So conclusions of this chapter: winds and currents both have similar diurnal components. They have similar times of peak amplitude, different spatial distributions of this peak amplitude, but the same spatial distributions essentially in terms of their their magnitude. They're highly coherent, which is sort of points towards, well, the wind is probably forcing the surface currents. They're deflected ahead of winds. The currents are deflected ahead of winds as expected, but by greater than what theory suggests in many locations. So we kind of get to the bottom of that. So for future work, we want to address the mechanisms that modulate this deflection angle and figure out what physics might be behind it at all frequencies, as well as the diurnal in particular. Okay, so let's summarize all 3 chapters in one slide if we can do our best. So we went over why these diurnal and semi-diurnal signals are important to satellite oceanography. Chapter 1, we covered our tidal harmonic analysis in general, as well as what we did to improve it for our purposes. In Chapter 2, we applied these tools to tides in the CCS, which are especially energetic in the semi-diurnal, and we found modulation that seems to be significant. And we looked at the spatial scales at which that modulation appears. And then in Chapter 3, we examined wind-current relationships, found coherence and behavior that points towards more complicated physics. then the usual theories. And so, so that is future work, I suppose, we can talk about. So let's do some acknowledgements now. This is standard procedure. First, we want to talk about our funding sources. Basically, it's all from NASA. NASA gave us all this money. There's the Future Investigators in NASA Earth and Space and Science Technology Award. This is a fellowship that funded me for 3 years. Thank you very much to my advisors for helping me, put together such a good application that they actually liked it. Also funding from these awards. I think only one of these awards funded me, but I'm not sure which one it was, so I put them both in. And then recently, the NASA Ocean Vector Winds Science Team Award has been funding me, and that explains why my Chapter 3 is more or less in line with that. And we also want to thank the 4 space agencies that came together to make the SWAT satellite. So it's NASA, CNES from France, Canadian Space Agency from Canada, and the UK Space Agency from UK. And the SWAT is sort of it's the reason why myself and a lot of other people even have careers. It funds a lot. It's funded a lot of people and a lot of interesting science, and it's just getting started. It's only a few months into its campaign, so we'll see what amazing science that it produces for us. I want to thank my 3 wonderful advisors, Sarah, Matt, and Bruce. They are the paragon of collegiality. They work together very well. They get along. They're humorous. They're empathetic. They've provided me excellent guidance. Not too much, not too little. They all have their strengths, but none of them have weaknesses, which I find very interesting. So just their strengths and their strengths. And they're all great on their own. If you were to have just one of them as your advisor, but they say that the sum of the whole is greater than its parts, something like that. And that applies to these as well. So all together, it's so much fun just to have our weekly meetings because they all get to they get along pretty well. I don't feel intimidated being the only student in a 4-person Zoom room usually. And then I want to thank the other committee members. We got Matthew Alford and Bill Coles. Sorry, Bill, I could not find any pictures of it other than this one of you online. It's on your website, so I yanked it. And you've both graciously accepted to be on my committee years ago and provided me feedback, and for that I am thankful to you both. I want to do a little acknowledgement for some research guidance to Merle Hendershot, perhaps the only person at Scripps whose enthusiasm for Baroque keyboard instruments exceeds my own. That's his shtick, and that's my shtick. Jinbo Wong, my future boss, if everything goes well, who's in the SWAT science team, and he's been very encouraging. Let me see. Ed Zarin has provided a lot of important feedback for understanding the tides. Brian Arbeck likewise. Florent Liard provided me sort of early access to the barotropic tide model to take a look at it a couple years ago, which was helpful. I don't know if it was really early access or if he just gave you what I needed without the hassle of me having to go through the correct channels, but it was useful at the time. And then the entire SWAT science team really, it justifies why I have a job. And that without all of them, obviously SWAT could have never gotten literally off the ground. Then I also want to acknowledge the people at Scripps Needs to Run. We got Tomomi, who is very important for the co-op department to operate. She's rectified so many budgets when I come back from a conference and I forgot to fill out a form. Gilbert, of course, is the VIP of the grad department. And then these 3, Anne, April, and Barbara, were all very important and helpful for me when I was doing renewal forms for my for the fellowship because I would have been lost without them. And then I want to acknowledge some members of the Gilly Maslow Cornell Nebulous group, past and present. And I probably didn't get everybody in this group, but these are sort of the names that came the most to mind. We have Bia Villas-Boas, Mara Freilich, Yu Gao, Cheng Pren, Salo Muller-Suarez, and Yao Yu. And I put them in alphabetical order because I don't pick favorites, but then I highlighted 2 of them because I do actually pick favorites. So my 3 office mates, 2 of them was Bia and Channing, Bia first and then Channing second. Bia, I would consider my academic big sister. She taught me everything I know about Unix operating systems and how to use Vim and how to use Git and just how to be a more efficient scientist. Now, that doesn't mean that I am a very efficient scientist, but she taught me how to be one. So in principle, I'm an efficient scientist. But no, basically, she taught me so much, and she's wonderful and supportive. She's now a professor. I'm so proud of her. She's wonderful. And then Channing, what an inspirational guy. He is one of the hardest workers I know, very productive. I feel like his PhD was basically 2 PhDs in one. And just sharing an office with him was just a joy because he also, provided interesting conversation and feedback and just, an overall good vibe. And of course, good vibes. I can't omit my current office mate, Jose Martinez Claros. who's not in this group, but you know, but oh, I guess it was mostly theme in the Gilly group. I'm sorry. Yeah, oops, I guess I got some details wrong. Anyway, because I think of you as more being, you know, Nick's postdoc. So, oopsie. Anyway, but you okay? So, well, your name's highlighted like that too. Anyway, you're an excellent office mate. You have provided me a lot of support as I, you know, have gotten my or progressed towards defense. And by support, I mean, you know, when I'm tired and stressed enough to just not come into the office at all, which is very nice. No, but I really enjoy it when you are in the office, though, too. So we've had lovely conversations. And then I, of course, want to thank my first year office mates, Jacob, Margaret, Teresa, Will, Mike, Ratnaksha, Curly Mike, and Jessica. Yes, his name's Curly Mike. Don't question it. They're, can you tell why? Yeah. So they're a lovely group of people to share the first year office with. You know, we tie-dyed. Oh, and Julia as the bonus 10th member, of course. How could I forget? I didn't. Your picture's here. And you know, we had fun. I don't using each other's weights apparently. Tie-dyeing shirts. You know, just doing math homework. And honestly, so when I started my time at Scripps, you know, I came out of physics, and I didn't really know that much about oceanography. I knew some earth science, but not much. And but a lot of these people did know a lot about oceanography, and they sort of really helped bring me up to speed. Even at a time when, you know, I was learning obviously from Scripps classes, it was really, you know, teaching me a lot, but they taught me even more. So they were like an extra class on top of it, but not stressful, which was nice. Let's see. I want to acknowledge my Dungeons and Dragons campaign group, also all Scripps people. We got Brendan, Sarah, Carrie, and Wendy, and Strider Weasel is way into this picture somehow. And this is when we were at the zoo, obviously. It's been a lot of fun. So during the depths of the pandemic, when the lockdowns were at its hardest, we were all sort of drifting apart socially, and we were like, and Brendan was like, "Hey, why don't we have a Dungeons and Dragons campaign?" He's been the dungeon master, and we've been doing the same campaign ever since. And because a lot of us have defended in the time since then, we haven't finished it. It's almost what, 3 years now, 2.5 years. We really got to finish it. We'll finish in a few weeks, probably. But it's been really fun hanging out with them every couple weeks or so on Dungeons and Dragons, just pretending to be elves, slaying vampires and stuff, you know, all that good stuff. And of course, I want to acknowledge my family. My dad, Mark, my mom, Sabra, they came 1,000 miles from Oregon just to be here today. And my brother, Strider, who came 1 mile to be here today because he lives in UT, because he lives in University City. They've been very supportive since day one, or I guess since day negative 9 months or so. Really, really kind. They never pushed me into a career that I didn't want to be in, which is really nice for my mental health. Maybe not so great for my bank, for my bank account, but super supportive. Never really questioned why I would do oceanography. You know, they also share a love for the planet and for science and for just intellectual curiosity. And they brought me up from the beginning, and it was really nice of them to do so. You know, they didn't have to, I guess. And I also want to point out particularly to my brother Strider, who in just a few short years went from whatever this is to being a full gainfully employed lawyer. And you might notice, yeah, this is just swearing in a year or two ago. And you'll notice University of San Diego. Well, that's in San Diego. So I went to Vassar College in 2011 as a dewy-eyed high school senior, freshly graduated. And then 2 years later, well, somebody else comes to my college. It's also Strider. He comes here 2 years later. Okay, well, that's fine. It's nice to have a brother at college. And then I went and did my Fulbright in Germany. And well, somebody else was doing his junior year abroad in Germany at the same time. It was Strider. So we hung out a lot in Germany. We gallivanted around Europe. And he spoke better German than I do. He's fluent and I'm not. And so that was fun. And then I came back and I started grad school here at Scripps. And I was like, okay, well, you know, I love my family so much, you know, it's hard to be far away from them, but I'm not as far as I was in Germany. 2 years later, Strider starts law school, and guess where he goes? Yeah, he goes just down the street. So, you know, it's been great, Strider, you following me around my entire life. And, you know, I guess I'll see you in Los Angeles sooner than later. Let's see. And of course, all my other friends at Scripps. So this is the part where a lesser soul would cry, but I'm not a crybaby. So I'm just going to talk about this like a normal person. So I went to sea once at a grueling 10-hour cruise that I slept through half of it, basically. That was a lot of fun. I stood in solidarity on the picket line with my union comrades on strike, providing emotional support via my bardic skills, obviously, playing my melodica. Let me see, tons of other friends. Some of you appear here multiple times, so I'm not picking favorites this time for real. in fact, apologies to the people I did not include pictures of because it's just hard to get good pictures of everybody. So I just got fun pictures of most of you. So, you know, let me see. So, first year office mates again, PO people in general, like a lot of PO people from many years here. Let's see, this was my first ocean science meeting with my compatriots. This is a picture of most of the people in the cohort 2 years below me, who I had the pleasure of being their teaching assistant. When Lynn taught PO 210, SIOC 210, that's the course. And it was a very fun class at TA, and you were all very smart, and it was very fun to grade your homeworks, and most of you had good handwriting, and not all of you. But it was fun. I eventually got to recognize you by your handwriting, actually. I've forgotten since, but let me see, anybody else I missed? Sawyer and Little Luke Pelosi are both some good friends who I first met as undergrads, and now they are grad students at respective institutions, and they are good friends to me to this day. A new baby yak named Jack is Mike's kid. I did not find the picture of me holding him, though. That was a really cute picture. And he unfortunately got cut off by another one, but yeah, cute little baby. Let me see, who else? Oh yeah, I did not actually drive the boat. This is me playing pretend, you know, pretending I have a job. So you've all had time to find yourself in this picture, so. Now it's my turn to turn around to you. Standing close to the computer so that the audience on Zoom can hear it. And actually, I want to really quickly make sure Zoom's set up so that I'm not like awkwardly trying to find whose messages or what. So let me just actually expand everything. Okay, but I think that unfortunately to you people on Zoom, we're gonna have to prioritize the people in the room first. So let's take questions. Lynn.
Hi.
Hi, Lynn.
First of all, you have a great future and rate my professor.
Yeah, unfortunately they took away the chili pepper feature for good reason. But I really was looking forward to having a chili pepper someday, maybe. That's not going to happen, but I'll just have to accept a hike. Thank you so much. Thank you.
You're welcome. So I have a question. How does this affect upwelling?
That's a good question, I guess. Let me think about it.
Or interact with it, or
interact with it. Well, I suppose if we look at chapter 3, where we have the wind blowing along, shifting along the currents. I omitted this figure, but there was a figure I had up here that I cut for time, where it just showed the mean flow in the California current. And as you teach in intro PO, it's like, well, the wind is mostly blowing to the south and then deflects the current offshore, and that leads to upwelling along the California coast, which is why it's so darn cold even during the summer. So I suppose getting a better understanding of the deflection of the current from the winds could lead to better, I guess, descriptive predictions of upwelling, I suppose. Also, I guess if this has implications for vertical eddy viscosity, maybe that would be important. I'm not entirely sure if that's a good enough answer, but that's what comes to mind right away.
Just curious.
That's interesting to think about, because if we have this data set at such high resolution, we might as well look at. I guess it could look like divergence of the vector fields and find the upwelling there.
Because you went all the way to the Ekman and sort of looking at the, it's just a really interesting plot of how the Ekman angle, where the angle to the wind, which may be Ekman or not, varies with frequency.
Yes.
And so your eddy viscosity must have some frequency, the eddy viscosity profile.
Yeah. Oh, yeah. It could be a frequency-dependent eddy viscosity, maybe. So that's right. That is something to think about. It could have to do. So maybe if you know the frequency profile of the wind that's blowing over it, you might be able to say something about the upwelling. Maybe. Yeah. Okay. Thank you. Anybody else? Okay, we got a lot. Oh my gosh, they're all coming up. See, once Lynn asks the question, everybody now feels comfortable too. I think, did Matt or Allie, which one raised your hand first? Matt, you're closer to me, so that's the tiebreaker.
Yeah, so great talk, Luke.
Thank you.
Congratulations. And so I normally think of Ekman like in a time mean, so should we necessarily be surprised that it doesn't fit Ekman that well?
Absolutely correct. We should not be surprised at all. In fact, if you recall from a few slides earlier, I even sort of, no, not this one. I italicized the word steady to draw contrast with what you're saying. It's like, yeah, this is a steady state thing, and what we're observing is by definition not steady state because we're looking at it breaking down the frequency domain. So you're absolutely right that there's going to be, it's going to be different from what we expect, which is why I wanted to compare it to sort of this more sophisticated frequency domain models that that Ellie Cohen Gilly did, but other people have done similar work and have actually looked at the analysis similarly with drifters and such. But no, you're absolutely correct that it would be different just because of the way that we're looking at it. And so any other differences that arise might be, it could be a frequency thing. In the mean, though, I didn't actually look in the mean at what the difference in angle is, so that actually would be interesting to see what it's all about. But yeah, I didn't look at the mean. I mean, maybe it would be. Nah, yeah, you can't really say from this. Like maybe as you approach the zero frequency, that is what the mean might be like. But I don't want to. No, I'm not going to say that. So I guess you could do this analysis without looking at it in the frequency domain and just find the mean angle deflection and see how it compares to Ekman. And I did not do that, and that might be worth looking at. So. If anybody here wants to do that for their PhD, I can tell you how to analyze this data without banging your head against the desk. Ali, you are the next person in line, I believe.
Yeah, thanks so much for your talk. It was great.
Thank you for being here.
I'm wondering if you have any thoughts or comments on what determines that spectral noise slope and what you do in red tide with some of those spectrum that have maybe varying slope.
Okay. So Ali's question was about how we determine the Let me actually repeat that for the Zoom people, and also just to make sure that I understand it. So what's it basically like? What leads to, or why do these different spectra have these different background slopes at frequency to the -2 or frequency to the -1? And how do we sort of determine that for red tide, or how we or
presume spectrum that has maybe a slope of -2 and then it shifts.
Oh, and then it shifts. Oh, within the same spectrum. Yeah, we can do that. So. As for why, okay, the first part is why it's like this, and I'm not 100% sure. I think it's just the energy of the underlying processes. Is it geostrophic? Is it ageostrophic? Those have different characteristic spectral slopes in the wave number domain, so I'm sure that they must have different spectral slopes in the frequency domain as well. So I guess that's just sort of an understanding of what's going on under the hood, I guess more theoretically. But what you're saying is, what if a spectrum has it's a negative, maybe it's gentle here and then it drops off faster. Well, you could do that using our methods. You'd have to understand how to build these matrices on your own because we don't have that automated in any sort of easy way. But you could take the spectrum, take the inverse Fourier transform of it, stick it in the matrix. And then you have your R matrix for the purposes of fitting. So yes, red tide does not require that your background noise be a straight line in log space. It could be arbitrary basically. Only limited by bandwidth because you can't have a 100,000 by 100,000 matrix you're trying to invert. At least not yet. So you'll have to do a little bit of numerical truncation along the zero lag to make sure, and then you need to make sure it's smooth so there's no spectral ringing. But yes, you could in principle, but what you would probably see is instead of this, if you took the Fourier transform of it back, it would probably look something like that because of the spectral ringing that you get from some truncation process to make things smoother, or computationally more efficient. Okay, is that good? Okay, who else has questions? David.
Yeah, awesome talk, dude.
Thank you.
I'm curious about the regularization that you used, and maybe you mentioned it, but how exactly do you choose a regularization for the Bayesian inference?
Okay, so let me actually go back to the slides just to, so the question is how we choose the regularization, the Bayesian stuff?
Yeah.
Yeah, let me see. So, you mean, oh yeah, so the regularization for the model components. So, what we do for red tide is we just take the power spectrum at these frequencies. So, and then we plug that into this P matrix, which we assume to be diagonal. It doesn't have to be, and this tends to be a small matrix, so you can in fact directly invert it without any sort of slick tricks. And the reason so if you recall during that example, get out of the way. If you recall during the example, there was a, I should probably share, am I still, no, I'm still sharing, am I still sharing screen? I think I am. Yeah. You see how, oh, this is 10 to the 3. So this is actually the inverse of the variance that we expect the signal to be at. And if you look at the spectrum at the M2, it's about 10 to the, oh, no, it isn't. Oh, no, because it's a power spectrum, because it's normalized differently. I think, okay, so if you were just worried about one frequency, or if you expected all frequencies to have a similar size in their amplitude in frequency space, then this is fine. But because we expect different tides to have different amplitudes, then we want to regularize it frequency by frequency. We want to make sure we want to regularize the M2 to be much stronger than we might regularize the much weaker N2 to be, for example. And that comes, and that sort of pops out of this derivation that I omitted, I guess, where you assume that it has some Gaussian distribution that has, and you're finding the mean, and that mean is found best by this. I don't know if I explained that very well, but basically, yeah, you don't want to over regularize some constituents versus others if you already know that one's stronger than the other. I guess that's the way that I think of it. I hope that was okay. Any other? Okay, more questions. There's got to be more. Okay, you both raise your hands at the same time. You fight it out.
Luke, you might have mentioned this at the start, but with the SWAT machine coming online, how does that resolution compare to the high frequency radar? Like, I understand that with SWAT you can go all of the ocean, not confined to the coast, but I'm wondering,
yes,
like, how does SWAT, or how do your tools and analysis compare to what's able to be done with SWAT?
Okay, good question, Monica. Thank you. Okay, so for those on Zoom, it was how does what SWAT's doing compared to the resolution and analysis and what we can see from high frequency radar, which is what I analyzed. And I think the resolutions seem to be kind of broadly similar. There's another thing I need to say about that, but first let's address the resolution. This is 10 times the spatial resolution according to them. I mean, I couldn't hear, but that was what the figure caption said. And these grid cells are about, I don't know, 20 to 30 kilometers. And so if that's, I don't know, 2 to 3 kilometers, that's pretty similar to HF radar, but there's some smearing going on. So that's actually not the resolution of this. I remember reading at some point that SWAT aims for like in the 15 to 30 kilometer resolution range. And that's actually pretty much the same as what we get from HFR. So the 6 kilometer grid is actually a lie. It's actually, it averages within a 10 kilometer search radius and then grids it to 6 kilometers. So the HFR, that I looked at is effectively 10 kilometers is like, the lowest that you can resolve a process at. And so it's pretty comparable. Now, the problem, of course, that maybe a lot of you have thought of or realized is that SWAT looks at sea surface height and high frequency radar looks at surface currents. And those are different quantities. They're related, but they're different. And so whatever interpretation that you have of surface currents, you're going to have to sort of make sure to not just, it's not a one-to-one translation to sea surface height. So okay, so resolution is similar, but it's a different quantity. So you'll have to be careful about it. There's also, like, if you look at certain regions of HFR, the triangulation that it does to calculate which way the vectors are pointing based on the geometry of your coastline is, they can be a little screwy. So that's why I cut off. The HFR goes out farther than I looked, but I don't want to go too far because it eventually just gets to be unreliable. So I think that answers that. Okay, and I believe that Hayden had another question. Yeah.
It seemed like this
Yes. Yes, and I can. Yes, and I can actually tell you why, because I fit this to the entire 2 years, and this is just the initial 1 month. And so there's a mean hidden in there that's shifted. It just happened to be higher than the mean here. The data happened to be higher than the mean, so the fit, which takes the mean out, is lower. So that's that, yeah. So just a simple linear sort of shifted down. I think that's what it is. There's also lower frequency variability that looks like it might be a mean, but isn't. But again, we didn't fit it in this particular. We only fit to those coefficients. And so there could be non-tidal energy or low period annual or semi-annual variability that's shifting that, but that's the explanation for that. Okay, do we have any online questions or any more in the room? Because Sarah's standing, so that must mean that she's probably getting ready to kick you all out.
There are no further questions. We will invite the audience to leave now, and hope to see you at Surfside at 1 p.m.
Bye.
It's the 7th, right? Yeah.
No, it's the 8th.
No, it's.
Oh, it's a different shade of black, though.
No one can tell from here.
Except for you.
It'll bother you for the rest of your life.
All right, 3, 2, 1.
Now I just everybody in the room, so me first turn on my camera. My phone is 5 years old, so it's going to be a little slow. Hold on, I got to delete that. Okay, now I have to turn around the lens. Now I need to turn it on to landscape mode. No, bubble mode doesn't work for self anyway, so let's just, most of you are in the picture, so. Okay, that's the best way.
Give us a smile.
Okay, first of all, no, I forgot my